Hi. Welcome. This is Laurence. He is a physics graduate student at FIU. He came to FIU in 2008. Did his bachelor's in physics, bachelor's of science in physics, and graduated in 2011 at age 19. And did research with Dr. Zhu in theoretical nonlinear optics. And now he's pursuing his PhD under Dr. Rajmani Narayan. And he is doing it in quantum chromodynamics, which is theoretical particle physics. He's going to give me a presentation. Bye.
Alright guys, so my presentation is on fictitious forces. Fictitious forces are forces that are due to an accelerating reference frame, due only to the fact that that reference frame is accelerating. The most common types of fictitious forces are going to be the Coriolis force and the centrifugal forces. And those are due to the rotation of the Earth. Not the Earth specifically, but due to any rotating coordinate system. Okay? So those are going to be the forces that I'm focusing my lecture on. Okay, so this lecture is just going to cover the basic theory and most importantly the derivation of the formulas for the Coriolis force and the centrifugal force. Then I'm going to talk about why they're important in everyday life. What consequences do we see in the world due to these forces? Okay, so we're going to start off the lecture talking about Newton's first law of motion. Okay, most people, when they take an introductory physics course, learn Newton's first law as an object that's in motion tends to stay in motion unless acted upon by a force. Okay, that loses all of the physical significance that Newton's first law has to offer. Newton's first law is more properly stated that there exists an inertial reference frame such that unless an object is acted upon by an external force due to an interaction of two particles, that particle's momentum will not change. Okay? He postulated the existence of these so-called inertial reference frames such that the only forces that exist in those reference frames are forces due to particle-particle interaction. Okay? This, along with his other two laws of motion, were published in 1687 in the Principia Mathematica. Okay? External forces, just for a bit of notation, I'm going to call as real forces. Okay? So, what is a fictitious force? Like I said, a fictitious force is a force that is due solely to the acceleration of a reference frame. These reference frames are called non-inertial. Okay? Non-accelerating reference frames are inertial, accelerating are non-inertial. Okay? They're also called pseudo-forces. Okay? These are forces that, like I said, do not arise from particle interactions. They arise only from the fact that the reference frame is accelerating. Alright. Inertial reference frames are the most important reference frames in terms of physics because of what I said. In an inertial reference frame, which is moving at constant velocity, the only forces that appear are forces due to interactions. Okay? So physicists, when they study interactions between particles, matter, subatomic particles, nuclear interaction, doesn't matter what kind of interaction it is, they deal with inertial reference frames. Because then they can isolate the force. Okay? A non-inertial reference frame, like I said, is one that is accelerating. Okay. So, to start the derivation of these equations, we're going to define an arbitrary position in a non-inertial reference frame. Okay? So this is the standard Cartesian coordinate definition of position. Okay? This is the position inside of the non-inertial reference frame. Lowercase I, J, K are for non-inertial coordinate systems. Uppercase I, J, K are for an inertial reference frame.
What's the difference between the two? How do you tell that?
You tell them because these would have non-zero acceleration or non-zero velocity action. These wouldn't be moving. An inertial reference frame is no, with respect to time. An inertial reference frame you can view as a reference frame at rest. If it's moving at constant velocity, that's for all intents and purposes the same as it being at rest. So these vectors would not change with respect to time if you were viewing them from a reference frame outside the group. Inertial reference frame. Exactly. This is a fixed. Exactly. That's what these are. It's an external inertial reference frame. Whereas these have a non-zero time derivative because these are accelerated.
And these frames usually relate to the Earth and some very far away.
Exactly. In my case, this reference frame would exist on the surface of the Earth where we are, but this reference frame would exist centered at the core of the Earth. So, to find the velocity of an object, you simply take the time derivative. Okay? This is where physics in inertial reference frames changes from physics in non-inertial reference frames. In an inertial reference frame, you would only have those, well, this doesn't really work, but bear with me. You would only have those, okay? In a non-inertial reference frame, you also have the fact that the reference frame itself is moving, okay? So these have non-zero time derivatives. Exactly. Because technically inertial reference frames can be moving, but moving at constant velocity. So you could just move at the same velocity with that reference frame, and it would look like it was at rest. Okay, so if you guys notice, we have these three time derivatives here. Okay, these in the form that they are useless to us. So we have to take a little deviation from what we're doing and derive a formula to express these in known quantities, such as how far you are from the center of the Earth and the angular velocity of the Earth. Okay? So, this capital IJK coordinate system is a Cartesian coordinate system that's inertial, centered at the origin of the Earth. Okay? And we have some arbitrary position vector of an object inside of our inertial reference frame. The unit vector of this object, right, is just the unit vector for its position. This object is rotating on the surface of the Earth. So this unit vector is also rotating on the surface of the Earth. This looks very much like our unit vectors for our non-inertial reference frame, which, as I said, exists on the surface of the Earth. Okay? So we're going to try to derive a time derivative of this unit vector. Okay? Omega sub e is the angular velocity or angular frequency of the Earth. They're the same because the Earth moves at a constant rate. All right, and theta is just the polar angle. Yeah.
Is this movement of the Earth with rotation?
Yes. It's rotating about the k direction, about the k-axis. Okay? Theta is not referred to as the latitude because the latitude, in terms of geography, is measured from the equator. Okay? But polar angles, as all of you guys know, are measured from the pole. Okay? So this is called the colatitude. It's the complement to the latitude. All right. So we're using a coordinate transformation to transform the position vector of our rotating object in our inertial reference frame from Cartesian to spherical coordinates. So this is the standard coordinate transformation. X and Y depend upon phi, right? And phi is the azimuthal angle, and theta is obviously the polar angle, like I said. So to find the unit vector, you simply divide the vector by its magnitude, which gives us this in Cartesian coordinates. Plugging in the coordinate transformations and taking the time derivatives give us these results. Okay? Theta doesn't change with time, r doesn't change with time. If you look at our picture, the particle is confined to a circle specified by a particular colatitude, but it's constantly changing its azimuthal angle. So the azimuthal angle is the only one that changes. Z is independent on that angle, so its time derivative is 0. Okay? Angular velocity is defined as just the rate at which the azimuthal angle is changing, and it's in the k direction. Okay? So, plugging in these results, you take the time derivative, r doesn't change with time. These are the inertial unit vectors, so they do not change with time. Okay, these are the ones that are fixed, centered at the core of the Earth. So you plug these in here and divide by r. Notice how if you take the cross product of omega of the Earth and the position vector, you get this. Using the fact that the coordinate transformations I told before, this is y times omega e just without the r. This is x times omega e without the r. So these two results are the same. And we can call the time derivative of any arbitrary unit vector as the rotation of the Earth crossed with the position in the Earth. Okay? So using that, all we do is we plug those definitions into that equation that we had originally. You guys remember this was the position with respect to time times that. You had these three, and then you had to correspond the complements from chain rule, which were the rate at which the unit vectors were changing. So we plug all those in. You can move the x into this cross product. The cross product is distributed. So you can move these, or associated. I don't know, but you move these in, okay? And then you do the reverse of the distribution of the cross product, because the cross product is distributed. So you can pull out an omega e, and you get xi hat plus yj hat plus zk hat. all crossed with omega e. Okay? I didn't have enough space to really fit that all in, but you guys can work it out on your own later. And that yields this result. Okay, now notice, this vector here, the one that only has the position derivatives, I called as r dot. Okay? dr dt is the velocity that an outside observer would see. Okay? And it includes the non-inertial parts. This velocity is the velocity that an internal observer would see. And it's simply just the rate at which the positions are changing with respect to time. So dot is just the rate at which the positions are changing with respect to time, which would be the classic sort of velocity that most people would be aware of. And dr dt is including the non-inertial parts. Okay, so once again, we have to take a second time derivative because we're looking for an arbitrary Newton's second law. Newton's second law is that the force equals mass times acceleration. So we need to find the acceleration. Okay, so you get the second time derivative of the position plus all of these terms. Once again, you have the time derivatives of the position. The chain rule will be the time derivatives of the unit vectors. And then so this is constant, so you don't take the derivative of that, or you just take the derivative of the position. Plugging in our old formula for velocity and doing the same sort of substitution here as before, we arrive at this equation. Okay? And we distribute the cross products, and we finally end with this. Okay, so this is our arbitrary acceleration. Once again, this is velocity inside of the non-inertial reference frame. This is acceleration inside the non-inertial reference frame. This is the acceleration outside. Yes, this is our double dot. This is our dot. Yes.
No.
Well, this. Yes, that's the second one. It's hard to see. It's there. Yeah, that's weird. Okay, this is supposed to be 2. It's a tiny, tiny little dot. It's really hard to see. Okay, but these two are both our double dots. All right. So, like I said, Newton's second law is simply that the vector force equals mass times the vector acceleration. Okay, so that's what we're trying to compose. We're trying to compose our own little version of Newton's second law inside of the non-inertial reference frame. So this is called the external force. Okay, that the net force, and the net force should only be the force due to interactions, equals the internal force plus the two non-inertial components. This is not how this is commonly written. Normally, these are flipped. We describe the internal force as equaling the external force plus the two non-inertial forces. Okay? So all I do is I subtract this side over here. And that's where these negatives come from. This second term right here, this negative 2m omega cross r dot, this is called the Coriolis force. Okay? And it's responsible for what I'll talk later, which is the Coriolis effect. This third term right here, negative m omega cross r, is called the centrifugal force. Okay? The centrifugal force is one that almost everyone is aware of as being a fake force, quote unquote. Okay? It's not that it's fake, it's just that it's fictitious. Okay? And those two words are not synonyms in this case. It is definitely real. You definitely experience it. It's just not a classical force because it goes away in an inertial reference frame. It only exists in a non-inertial reference frame. Okay, so internal versus external force. The internal force is the total force that an object inside of a non-inertial reference frame will feel. Okay? This includes all real, as I called them, forces, as real as defined by Newton's first law, and all fictitious forces. The external force is the one that appears in Newton's second law. Newton's second law says the sum of the external forces equals the mass times the acceleration. Okay? And